Hello students, welcome to the physics course. We will continue with the lecture on blackbody radiation in quantum physics. Before I start today's lecture, let us summarize what we have done in the first lecture. So in the first lecture, we have seen that any body can absorb as well as emit radiation at any temperature. We have also discussed what is meant by the emissive power and absorptive power of a body. We have stated the Kirchhoff's law of radiation, which states that the ratio of the emissive power to the absorptive power is a constant, and that shows that a good emitter is a good absorber. We have discussed what is meant by a black body. So a body which can absorb all radiation that is incident on it is a perfect black body, and a perfect black body is a perfect emitter and a perfect absorber. And we have also discussed some examples of black body. Now in today's lecture, I plan to discuss with you the method by which we can create a black body in the laboratory. And then we will see how this black body spectrum looks like and what are the experimental observations from this black body spectrum. We will then discuss the Wien's displacement law and the Stefan-Boltzmann law. So in laboratory, the standard way in which we can make a black body is that we take a cavity. It may be a spherical cavity or a rectangular cavity with a small orifice on it, and the inside of this cavity, the inner walls, are coated with a material called lampblack. Now as the radiation enters through this small hole inside the cavity, due to this lampblack coating, it undergoes multiple total internal reflections at different surfaces of the wall. And so the entire radiation gets captured inside the walls of the cavity. So this small orifice acts as a perfect absorber, and the radiation is absorbed inside the walls of the cavity. Then next is that once this radiation is absorbed, then how it will emit the radiation. Now since the radiation is absorbed by the walls of the cavity, this causes a heating of the cavity walls. And this excites the atoms lying on the surface of the walls, and the atoms start vibrating at frequencies characteristic of the walls of the cavity. So these atoms then re-radiate the energy at this new characteristic frequency, and the radiation comes out through this orifice. The nature of this radiation leaving the cavity, that will depend on the temperature of the cavity. And the emitted radiation characterizes the equilibrium temperature of the black body. Now the radiation that comes out of the cavity, that is detected by an infrared spectrometer using a bolometer as a detector, and this is how the black body spectrum will then look like. Here we have plotted the intensity versus the wavelength, and you see that you have the radiation in the ultraviolet region as well as the infrared region and also in the visible region. But in the very low wavelengths and high wavelengths, the intensity is less and the intensity is maximum at a particular wavelength. And this is how the room temperature radiation will look like. Now let us discuss what are the observations that we get from this black body spectrum. So for a given temperature, the intensity is becoming maximum for a given wavelength, as we can see. So we have plotted here the graph for different temperatures. And as the temperature is decreasing, the maximum value of the intensity is also decreasing, and the total energy that is being emitted is decreasing because the area under the curve will give the total energy that is emitted, and the area of the under the curve is decreasing as the temperature is decreasing. The value of the wavelength at which the intensity is becoming maximum, that decreases as the temperature increases. This wavelength at which the intensity is becoming maximum is called the peak wavelength, and as you can see here that as the temperature is increasing, the value of this peak wavelength is decreasing. And the curve is getting infinitely close to the x-axis at the higher wavelength region but is not touching the x-axis. So from this spectrum, now we can write down the Wien's displacement law, which states that lambda max T is equal to some constant, and the constant value is as shown here. This lambda max is the peak wavelength, the wavelength at which the intensity is becoming maximum, and T is the absolute temperature of the black body. So according to this law, lambda max and T are inversely proportional to each other, And as the temperature increases, the peak is displaced to shorter wavelengths. Now let us see some application of this Wien's displacement law. So if the temperature of the Earth's surface is 310 degree Kelvin, then if we put that value of this temperature in this Wien's displacement law formula, we get the wavelength that is being emitted by the Earth's surface, and we see that the radiation is in the infrared region. Now if we think about the temperature of the sun's surface, say 5800 degree Kelvin, and if we put this value of this temperature in this formula, then the wavelength that is emitted by the sun's surface is of the visible region. This can also be used to determine the stellar temperature, the temperature of the star. So if the wavelength of the light emitted by the star, if we put in this formula, then the temperature of the star can be determined with the help of Wien's displacement law. Another law, radiation law related to black body, is a Stefan-Boltzmann law, which states that power, that is the energy per unit time per unit area radiated by a black body, is proportional to the fourth power of the absolute temperature of the body. So T here is the absolute temperature. And the sigma is a proportionality constant. It is called the Stefan's constant, and the value of sigma is what we see over here. So now if we just summarize, black bodies do not reflect or transmit any radiation. They absorb the radiation and they re-radiate the radiation. But the emission characterizes the black body only. And the emission from a black body depends on its temperature. So at room temperature, we or different bodies, they radiate in the infrared region. Objects at around 600 to 700 Kelvin, they start to glow. And at very high temperature, the objects may become very white hot. So with this, I have come to the end of this lecture. Now in the next lecture, I will discuss with you the classical laws of radiation which try to explain the black body spectrum. But the classical laws fail to explain the black body spectrum. So we will discuss also the failure of the classical laws, and that led to the quantum hypothesis by Max Planck, and we will discuss the Planck's law of radiation in the next lecture. Thank you.